One of the most beautiful and useful of minerals is rock crystal or quartz. Quartz is brilliant and clear in its pure form, but it takes on colors and tints when it contains traces of impurities. Quartz grows in many forms and makes up a very large part of the crust of the earth. It is also known under other names such as amethyst, agate, and rose quartz. Once used principally for decoration, it is today more than a thing of beauty. When cut into tiny pieces, it controls the frequency of radio transmission and reception. Crystal wafers, precisely cut from the natural mineral, set the radio channels for the armed forces, much as push buttons select the stations on home sets. They do it more simply and with greater accuracy. In war, they provide quick and certain means of communication between fighting units. While experimenting with piezoelectric crystals during World War I and seeking a method of locating submarines, Professor Cady recognized in quartz the key to the hair-splitting accuracy which crystal controls provide for radio today. Piezoelectricity, a property of quartz and of certain other crystals, was discovered by the Curie brothers of France more than a half a century ago. The problem of getting radio plates out of the rock can be understood by considering this wooden model. We desire a little square plate cut at just the right angles of tilt and of turn with reference to the natural boundaries of the perfect crystal. The crystallographer speaks of axes which are perpendicular and parallel to some of these faces. We have to saw through the quartz at angles which are exactly right to have the finished plate behave properly in the radio set. The plate whose boundaries are traced in pencil on this wooden model is known as a GT cut plate because of its particular orientation in the mother rock. Holding angles of cut to extremely close tolerances is one of the cardinal principles of good crystal plate manufacture. Precise orientation seems simple when the quartz has its natural faces. Fortunately, even in rough faceless quartz, the layer structure of the atoms is still there as a guide. This structure can be picked up with X-rays. In the receiving room of the factory, the cases of rough quartz are opened and a preliminary sorting and inspection of each piece takes place. Practically all quartz used in the manufacture of radio crystals comes from Brazil. Its value to the nation is so great that each bears a label of its importance. The quartz is roughly sorted according to size, shape, presence or absence of natural faces, and quality. We do not find many ideally shaped quartz crystals in the shipments. Crystals that show more than a few of their original faces are uncommon. With most pieces, these faces have been broken off in mining. Others have been rounded and smoothed by rolling on the bottoms of streams. A few are fairly symmetrical with faces clearly formed. Sometimes quartz has a reddish appearance on the surface, and occasionally it is a smoky color throughout. But color is of little importance in making radio plates. After preliminary sorting, there is a thorough inspection for cracks, optical twinning, inclusions, and other internal imperfections. This is done in an immersion tank filled with a special type of mineral oil. The inspector submerges each quartz crystal and rotates it in a strong beam of light. Under oil, the surfaces of the quartz vanish, letting the interior imperfections come to light for the inspector to observe. From the character of these imperfections, he judges the usefulness of each piece. After the quartz has been examined under oil in polarized light, it is marked according to its quality. The grades and sizes after being classified are placed in storage trays, and these, quickly identified by color or other means, are stacked ready for manufacturing. From the storage trays, the racks are carried to the orienting and sawing departments, where the manufacturing process begins. Pieces for the day's production are selected, and the method of cutting which will produce the greatest number of crystal oscillators is decided upon. The quartz is again submerged in oil so that the optic axis may be located and marked. The optic axis is found by locating certain bands of color which are formed when the quartz is examined in polarized light. Also, in polarized light, certain types of imperfections in quartz are revealed by other patterns in color. A striking example of this latter is seen in this flat plate. The triangular patterns, which keep their forms though the colors change with the change of the lighting, indicate twinning of the quartz. Twinning is an imperfection which must be discovered and twinned regions avoided in the finished plates. By means of such color effects, the operator has now decided where the optic axis lies and is marking a guideline on the surface. For ease in guiding the sawing operations to come, he paints a series of dots along the axis to make the direction stand out. The rough quartz is next cut by the saw into small pieces. The saw is a rotating disc of copper or steel charged with diamond powder along the rim. As the revolving blade starts into the stone, a thin stream of cooling liquid is directed across it. Special saws are among the many developments which have been made during the war to facilitate the manufacture of quartz plates in large quantities. The quartz is harder than steel, but the diamond-edged blades quickly go through the large pieces. For successful cutting without undue waste of material, the saw blades must be as thin as possible and quite free from vibration. A stone of this size is cut into several slabs, and for convenience in handling, each of these slabs will in turn be sliced into smaller pieces. Precisely and quickly, the blade of the saw cuts through the quartz. Note here how its shadow appears to mark the way. Sawing so far seen has been of the rougher sort along the approximate axis of the mother quartz. The final slicing of this bar into wafers is an operation of more precision. And in order to keep record of the orientation of the bar in relation to the original mother quartz, a reference direction is marked on the surface. As a first step, we need to identify the electrically negative and positive faces of the quartz bar. This is done by squeezing it gently under a lever arm and measuring the electrical charge on a vacuum tube voltmeter. The second step in lining up the quartz for cutting is made in a conoscope. Direction marks are again made on the bar, and it is placed in an electric oven to be heated in preparation for mounting. The warmed quartz is taken from the oven, coated with shellac and hot cementing compound, and its piezoelectrically negative side mounted down against the faceplate of the jig. For accurate determination of the angle for cutting the wafers, it is necessary to provide for both easy adjustment and firm clamping of the quartz. It is mounted on a jig, such as the one shown, where the quartz may be oriented in any direction. It is to be finally locked in just the right position for the saw cut. The quartz, firmly bolted on the adjustable jig, is again submerged in the oil of the conoscope. The quartz is to be aligned in relation to the internal structure of the quartz rather than to the surfaces of the rough bar. With this flat bar, the optic axis shows itself as the center of a very perfect set of colored rings which appears in the eyepiece. These rings shift as the bar is turned ever so slightly. The task is to center the rings on the crosshairs of the eyepiece. When this is done, it determines the optic axis with good precision. For final and still greater accuracy, adjustments are made by means of X-rays in the darkroom. The X-ray machine is so set up that when the quartz is tilted to its exact position for sawing the BT cut crystals, a characteristic pattern of spots is reflected from the atoms of the crystal, making a sort of picture of the positions of the atoms. These spots are not visible to the camera, but appear on the screen before the operator. When satisfied that the position is correct, the operator locks the jig in proper adjustment and places it on the shelf ready for the wafering saw. In looking back, we have seen the mother crystal sawed into slabs, and one of these in turn into several bars. Wafers are next to be precisely cut from one of these bars on the basis of the electric, optic, and X-ray tests which we have just seen. On the bottom of the steel jig upon which the crystal is mounted is a groove that fits accurately into a runner on the saw table, ensuring that the quartz cut will be in accordance with the X-ray measurements. Vertical arrows have been drawn on the quartz in 2 previous operations so that the crystal would not get inverted. After the jig is firmly bolted to the saw head, a preliminary cut is made to remove the end of the bar, and again an identifying arrow is drawn to keep track of the up direction of the first wafer to be cut. The rough wafers are rarely more than 1/16 of an inch thick, and it is quite an art to saw them thin and true from this hard and brittle material. The final finishing of the crystal plates to thickness will be done in grinding and lapping machines, and the time for this operation will be greatly shortened and much material will be saved if the wafers are initially cut thin and accurately by the saw. Quartz crystal manufacturing makes important use of X-ray machines as part of mass production. X-rays permit measurements of angle in the crystal to be made much more accurately than is possible by other instruments. This X-ray machine is equipped with an electric meter to pick up the reflections from the atoms. Although the orientation of the bar before cutting was made with great care, the tolerances of the radio plate are so small that it is desirable to check the angle again after the first wafer is sawed, to make certain that if there is a slight error, it will not be repeated in other wafers sawed from the same bar. After the first wafering cut has proved to be accurate, the entire quartz bar will be cut up into wafers. In order to find any defects or twinning which may have escaped previous tests, The wafers are now etched in a safety etch bath Motor-driven arms agitate the solution during etching. After an hour or so in the etching bath, they are washed and then cleaned with alcohol. The etched wafer has a white surface. The difference between an etched and an unetched wafer is readily seen. In looking for twinning on etched surfaces, the inspector sits before a small turntable and rotates the wafers under a concentrated spotlight. Differences in sheen of the surface bring to light any twinned regions. Here are several examples of twinning as seen on etched wafers. The twinned portion is marked out with a pencil. When the wafer is being cut into quartz plates of the required size, the twinned portions will be avoided. The wafers are again examined, this time in the polariscope, in order that when square plates are cut, their edges may be lined up with the electric axis of the quartz. A line indicating this direction is drawn upon them. In marking out the wafers, they are squared up with this line. The workers space their lines carefully so as to get as many plates as possible from the wafer. The two sides of the squares, which have been outlined in pencil, are now cut one at a time by rotary dicing saws. The wafer rests flat on the table as it moves under the whirling saw. The table moves toward the blade, and the wafer is neatly and quickly cut through. Wafers marked for several blanks are here held in the hand for the separation cut. For speed in cutting and to reduce breakage, the partly cut wafers are next stacked and held together with paraffin. The uneven sides of the bundle are cut in the mechanical dicing saws. After one side has been cut, the bundle is turned and the operation is repeated. After the bundle has been cut, the paraffin is melted and removed from the square blanks. They are sorted according to thickness and are ready for the first stage of grinding and lapping. In the first lapping machines, coarse blanks are ground down to a thickness of approximately 17/1000ths of an inch. The lapping machines are flat cast iron discs grooved on the surface. On the bottom disc is placed a thin zinc holder with pentagonal openings. When this holder is secured in position, the rough blanks are inserted in the openings. The top grinding disc, which is also grooved, is now placed carefully on the blanks. In the high-speed lapping machines, the bottom plates of which revolve swiftly, the blanks are lapped in approximately 1/10 of the time formerly required. Lapping is done with a comparatively coarse silicon carbide abrasive. When the desired time of grinding is completed, the machines automatically stop and the blanks are removed. They are cleaned and prepared for grinding of the edges. In grinding edges to uniform size, the blanks are again stacked in bundles and cemented together with paraffin. The four edges of the stack are ground until they are smooth and even and have the desired dimensions. The blanks are uncemented by soaking in boiling water. Then they are cleaned and ready for classification. A dial-type micrometer speeds up this classification. They are measured and grouped by thousandths of an inch. A given number of blanks of the same thickness are taken for the final delicate machine grinding. From the classification room, the sorted blanks are sent to the dust-proof precision lapping room, where they will be mechanically ground fairly close to the desired frequency. The first operation in precision lapping is the thorough washing of the machine and the holders to remove all old abrasive. The eccentric motion of the holders ensures uniform grinding of all blanks. After washing, the holders are turned before another lapping begins. The selected blanks of the same thickness are distributed in the holders. Spoonfuls of fine abrasive are next poured onto the blanks. After spreading the abrasive carefully over the blanks, the operator gently feels to be sure that all of the blanks are in place. The top lap, which is grooved like the bottom one, is now placed on the machine. The clock is started and set for the required time that the machine is to operate. When the time of lapping has ended, the operator deftly lifts off the top lapping plate and removes one sample blank from each of the 5 holders. These are cleaned and tested between metal electrodes in an oscillating circuit. Upon adjustment of the dial, the meter tells the activity of the blank, and at the same time, an audible tone indicates the frequency by comparison with the standard. If the blanks tested are close to the desired frequency, all of the remaining blanks are removed from the machine and sent to a second classification department, where they will be tested individually. In this second classification department, each blank is tested electrically and sorted according to frequency in preparation for the final finishing to specification. The thickness of the crystal plates determines the frequency. The thinner the plate, the higher the frequency. In the final finishing department, the crystals are etched, first in mass and then individually by hand, to bring them up to the various specified frequencies. Preparatory to the mass etching operation, the crystals are then stacked in notched Pyrex glass racks and are given a final cleansing in a concentrated chromic acid solution. The crystals are first thoroughly cleaned to remove abrasive and oil left by the machine lapping process. The racked crystals are transferred into successive shallow tanks in which the acid is washed off. The crystals are now etched in a solvent for quartz known as frequency etch for a sufficient time to bring their frequency close but not quite to the final frequency desired. The crystals are then removed from the etching solution and are thoroughly washed, first in a neutralizing solution and then in pure water. At this point, the crystals are taken out of the racks and after their frequencies have been checked, are issued to the hand finishing operators who make the final individual adjustment of frequencies. The operators are seated at tables and are busily engaged in one of the most delicate of all operations in the manufacture of crystal oscillators. The final adjustment of frequency of the crystals is done with such great precision that the operators have been aptly named the millionth of an inch girls. Each finishing position is equipped with a small sink hot running water, compressed air, small dishes containing etching and neutralizing solutions, plastic tongs to hold the crystals, a revolving drum-like edging device, and a comparison oscillator. The crystal is first thoroughly scrubbed with a brush and soap solution. A thoroughly clean surface is necessary if the etching is to take place uniformly. After the scrubbing, it is well rinsed in water. It is thoroughly dried with compressed air and placed between electrodes. The crystal is then measured in the oscillator to determine the amount of frequency that must be etched off to reach the precise desired value. The activity of the crystal is also checked. In the instance seen, the crystal activity is found to be low. To increase the activity, the operator lightly laps the edges of the crystal by holding it within the abrasive-lined rotating drum. The crystal is now gripped in the plastic tongs and is placed in the etching solution for the required time. While the crystal is etching, the operator cleans and dries the electrodes. The etching solution dissolves quartz from the surface of the crystal, making it thinner and thereby increasing the frequency. Also, by removing the damaged surface layer produced by machine lapping, etching increases the stability of the finished oscillator plate. The crystal is removed from the etching solution, washed, neutralized, again washed, and its frequency measured to find how close it is to the desired value. The frequency is still found to be low, so that the crystal is again scrubbed, etched, washed, dried, and remeasured. The frequency is now found to be within the tolerances, and the crystal is put into its permanent holder. The frequency and activity are again checked. At this stage, the crystals are all put through a drop test and a vibration test to ensure that they will maintain their performance under the production tests. The crystals are first dropped through a zigzag funnel-like contrivance. The wooden cover of the box has been removed to permit this photograph of the operation. The intense vibration found in aircraft or other military vehicles requires that every crystal be securely fastened within the holder and not shift its position or frequency. The crystals are now mounted on a broad horizontal rack where they are mechanically vibrated for half an hour. The intensity of the vibration is seen by the behavior of a glass of water, which has here been placed on the vibrating table. The crystals are now taken to a calibration room where an exact measurement of frequency is made by direct comparison with the standard frequency using a cathode ray oscilloscope. The rotation of an ellipse in the oscilloscope will indicate the frequency down to 1/1000th of 1%. The accuracy is far beyond that required when the ellipse turns as slowly as shown here. The crystals that pass the oscilloscope test have the covers of their holders tightly screwed down. Frequency identification plates are then attached. When the crystals are calibrated, it is found that a small proportion have, for one reason or another, slightly higher frequencies than are desired. These crystals formerly were sent to salvage and were relapped and finished to the next higher frequency channel. Very recently, a revolutionary new technique has been developed in the Reeves Research Laboratory, by which it is possible to reduce the frequency of a crystal whose frequency has been carried too high. In practice, the amount of decrease in frequency needed to bring the overshot crystal back within tolerance is measured. The crystal is then removed from its holder and placed in a slide which centers it in a powerful beam of X-rays. When the slide is pushed in, a switch automatically turns on the X-ray beam, and similarly, when the slide is removed, the X-rays are turned off. The X-rays lower the frequency of the crystal by altering certain atomic properties of the quartz itself. The amount of frequency change is governed by the length of exposure to the X-ray beam. The operator times the exposure to give the desired change in frequency, and the crystal is then removed from the X-ray unit, placed in its holder, the frequency measured again as a check. The recovered crystals are now added to the stock which did not need the X-ray treatment, and all are ready for their final factory tests. The activity and frequency of each crystal are measured and recorded while it is being subjected to temperatures ranging from -55 to +90 degrees centigrade. Air circulating over dry ice in one part of the box simulates temperatures in the stratosphere. Heating units in another part of the box bring the temperature up to heights much greater than those expected under normal operating conditions. The performance of each crystal is measured every 2 degrees over the temperature range, and a complete record of it is made. Thousands of crystals are tested this way every day, for upon these and other tests depend the certainty and accuracy of radio communication and the lives of American airmen and those of our allies. The record charts of each crystal are checked. Those that pass are okayed and sent on. Any crystal whose chart indicates a failure within the temperature range is rejected. At the completion of the temperature test, a final production test is made to see that the holder is tightly sealed against leakage. The crystals are plugged in groups of 60 into a rack which is enclosed in a glass vacuum chamber covered with wire mesh for protection. The air is pumped out as shown by the changing level of the mercury manometer. A potential difference of more than 1,000 volts is placed across the electrodes. If the holder leaks, an ionization current registers on the dial. By means of a selector switch, the operator can measure each of the 60 crystals in turn. At the completion of the measurements, air is let back into the vacuum chamber. When room pressure is attained, the bell jar is lifted and the crystals removed. The crystals are next turned over to the signal corps inspectors. They first undergo electrical inspection, where the units are tested in standard test sets, which simulate the actual conditions under which they will be used in radio sets. When they pass the electrical tests, they are sent on for mechanical tests. The inspector examines each case, looking for any irregularities. Upon completion of the final signal corps inspection, the crystal units are packed. Each crystal unit is placed in a separate box. Before closing the cover, another inspector checks to be certain that the frequency marked on the box is the same as that marked on the crystal unit. The boxes are then closed. The final signal corps check is made in the shipping room as the cartons are filled and sealed. When a carton has been filled, the emblem of the signal corps is stamped on each seam, the emblem of approval, the emblem under which crystals go to war.